Whenever we are given k-sorted list or k-sorted array and we are asked to merge them or find the nth smallest element within those lists and arrays and elements, we should start thinking about using k-way merge pattern. So here is an example. We are given an array of linked lists. We have 3 linked lists and we want to merge them in order to have a one single sorted linked list. Each of these linked lists are sorted. Now, what we can do is that we can use the k-way merge pattern to solve this problem. And this is how it works. So we know that each of these lists are sorted. The first element, the smallest element, should be among the head of these lists, right? So we have 3 elements at the beginning, 1, 1, and 2. Now, what's the smallest element here? It's 1, either this one or this one. Let's go with this. So now that we use this one, we go next. Now, again, among these 3 elements, which one is the smallest one? It's 1. The next element will be 1. Now we go next. Again, between 1, 2, and 3, which one is the smallest? It's 1 again. Between 2, 3, and 4, it's 2. Between 3, 4, and 4, it's 3. Between 4, 4, and 5 is 4. Either this one or this one. Doesn't really matter. Let's go with this one. Again, between 4, 5, and 6, it's 4. Between 5, 5, 6, it's 5. Then between 5 and 6, it's 5. Again, we reach the end of the list here. And then the only element that's remaining is 6. So now there's no any other element left. So we're done. And we end up having a sorted linked list. Basically, we merge all these 3 linked lists into one big sorted one. So you saw that at every step, we go through the list. Here was basically 3 elements because we had 3 linked lists. And we found a minimum at every step. So this is going to be okay if we have, like, let's say 3 for a few number of lists or array. But if we have a large number of lists, then it's not going to be efficient. What should we do here? Instead of going through all the lists and find the minimum, there should be a better way to find a minimum. And for that, we are going to use heap or mean heap in this case. So I'm going to describe very briefly what heap is, and for further information, you can check the link above to learn more about heap. So we have mean heap and max heap. So basically heap, or let's for now consider mean heap, is the tree-based data structure that gives us access to the minimum value of the list in constant time. Okay, so if we have, let's say, 4, 2, 5, minus 1 element, and we heapify these lists, it can be something like this. Heap has 2 important characteristics. So heap tries to be balanced, but sometimes if the number of elements is even, it cannot be balanced. The other feature of heap is that for mean heap, the parent, it's always less than or equal to its children. In max heap, it's opposite. In max heap, parent is greater or equal to its children. So let's consider just mean heap for now. Now, what will happen if we append or add to this list? So let's say we add 6 to this list. So 6 will be added at the back of the heap. Again, to keep it balanced, it will be added here. And now we check whether its parent is less than or equal to its children, which is the case. So we are good. Now let's add 0. So again, to make this balance, so we add 0 here. Now let's check this condition. The parent of 0, 2 is not less than or equal to 0. So we swap them. Again, minus 1, the parent of 0, is less than equal to 0. So that's good. So we stop here. Now, what if we pop the root? So I mentioned that we only access to the root. We pop minus 1. Now the root is empty. We have to fill it up. What we can do is that we replace the root with the last element or the element in the back of the heap, which is 2 in this case. Now we try to push 2 down to satisfy this condition. So is 2 less or equal than its children? No. So then what's the smallest child of 2? It's 0. So we swap them. So is 2 less than or equal to its children? Yes, that's good. So we are done. As you can see, we pop -1 and the heap organized everything again, and now we have access to the minimum value after -1. So the point is that min heap gives us access to the minimum value at every time, so we don't need to search for the minimum value in the list. The max heap, on the other hand, gives us access to the maximum value. All right, so now that we know how heap is working and we know how to approach this problem, instead of keep searching for the minimum value at every step, we just use heap. Now let's see how we can code this up in practice. Here's the problem. So we are given an array of k linked lists, and each linked list is sorted in ascending order. We want to merge them. So here's an example. 1, 4, 5 is one list, 1, 3, 4 another list, and 2, 6 another list, and the output would be 1, 1, 2, 3, 4, 4, 5, 6. So let's define our linked list class first. Each linked list element has a value, and next. To be able to sort and compare the linked list, let's define our less than method. Okay, as I mentioned, we are going to use heap. So for that, we import heap, heap q, heap push, and heap pop. Now let's define our class. Our class is to merge lists. So we're given an input. So first of all, if our input size is empty or has only one element, means that we have only one list, and we know that it's already sorted, so we just need to return. We don't need to do anything, we just return input. Now, so let's have a dummy head here that points to the beginning of our results, of our output. And our current pointer, which at the moment is at dummy head. Now, so I mentioned we should have our min heap, which is an array here. Now we go through the list and put the first element of each of the lists, like here is 1, 1, and 2, to the min heap. We push it to min heap. Heap push min heap L. Okay, and it automatically put the linked list node with minimum value at the root. Now we say while len of our min heap is greater than 0, do this. We basically read from the root, and we add this node to our result. Current.next is node, and we go one step forward. Now we check if our node that we just read from the heap has a next value. We push it to the heap. But if not, we just don't push anything. We keep doing that until we go through all elements and nothing else remains in our min heap. And then at the end, we just return our dummy head.next. Now let's see if it's working. Okay, so we have linked list 1, 4, 5, and then 1, 3, 4, like this one, and then 2 and 6. And we make it a list of these 3 linked lists and call our function, and we get the output, which is a linked list, sorted linked list, and we go through this output and print it out. So let's see if it's actually sorted. It's 1, 1, 2, okay, 3, 4, 4, 5, 6. Perfect, it's working. So now let's check the time complexity and space complexity. So at every time that we push or pop from the heap has to update itself to make sure that minimum value is on the root. And for that, it actually traverses the height of the tree. So if we have n elements in the tree, and we know that it's a balanced tree. So if you have n elements of the tree, the worst, like when we add or when we push an element down or push an element up to the tree, we know that it's the time complexity for that is log of n, the height of the tree. Because we have at most 3, like in this case, in this example, we have 3 linked lists, okay, at this point, it'll be O log of 3, okay? So if we have k lists, our heap will have k values at most, okay? So popping and pushing to the heap will take log k time. Now, how many times we do this? How many times we push and pop from the heap? Well, it's a number of elements in the whole input. If we have n elements in general, the total time complexity would be n log k, where n is total number of elements and k is number of lists in input. And the space complexity, so if we ignore the output, the space complexity would be just our heap, right? So it would be O of k. So that's it. If you found this useful, feel free to subscribe and like, and I'll see you next time.